Well, it's time for us to find our center. We're doing problems involving center of mass. So as with all problems, make sure you do as many as you can, because the more that you do, the more comfortable you'll become. And if you're following along with the video, make use of the pause button. See a problem that you like? Pause it and try it yourself. And then that problem will become yours, because now you've mastered it. If you ever need any help, just unpause. I'll come along and we'll figure it out together. So, with that, let's begin. Our first problem. A rod has density delta x equals 1 plus 2x, where we go from 0 to 2. The problem. Find the total mass of the rod and find the center of mass of the rod. So, when we talk about a rod, what we're really saying is it's 1D. So, we model it like a line segment. So pictorially, we can say, well, it's a line segment. If we want to think of it as varying density, we'd say, well, what's happening? At 0, where we start, it's a little bit thick, but it gets thicker as we head over to here towards 2. So that's sort of our picture we should have in mind. So there we go, 0 to 2. So what do we need to do? Well, let's look at our two problems. We have two, right? Mass, center of mass. Now mass is pretty what do you do? Well, you add up. That's what we do when always we're doing integration problems, is we're adding up from the start to the end. And then we have our density and our length. Because for one dimension, density times length, that's a one-dimensional thing, that gives us the mass of our little part. Well, for us, integral 0 to 2 of 1 plus 2x, that's our density, and then our length is dx. Well, that's not so bad. That's x plus x squared. From 0 to 2, plug in 0, you get 0. Plug in 2, you'll get 2 plus 4, which is 6. All right, so done with the mass. Now we go to the second part where it says, where's the center of mass? Okay, so for that, we should take a moment, which means we need to have a term. We call it the moment with respect to 0. So we'll denote this as m sub 0, or if you like, m sub origin. Where is our location in terms of the origin? So the difference between mass and moment is you have this extra term. And I like to call it location. You can call it distance, whatever helps you understand the idea. So there's a location, a density, and a length. So most of it's still the same. How do you think of location? Well, location is, think of it as you have a little tiny part here. So here's a little tiny part. It's located at x, and we always do it in relationship to something. So that's the origin, or 0. So for our location, our distance, where we are at, is x. So we have x times 1 plus 2x. So location, density, length, dx. Length being the length of a very tiny part. And whoops, I should have updated. Our bounds aren't a and b. They're 0 and 2. Well, we'll pretend like that's a 2. All right. Well, okay, so that's integral 0 to 2 of x plus 2x squared. We can integrate that. That's a half x squared plus 2/3 x cubed. And evaluate 0 to 2. All right. Well, plug in 0, you get 0. That's good. How about 2? 2 squared is 4 times a half gives 2. 2 cubed is 8 times 2 is 16. So we have 16 thirds. Now we can put this over a common denominator. 2 is the same as 6 thirds. So we have 6 thirds plus 16 thirds, giving us 22 thirds. All right. Now, that's not our center. How do we know? Well, look at it. That's a 7. Now let's say our center of mass would be like way out there. It'd be off the page almost. Forget it. That's not right. Remember, how do you find the center? It's a weighted averaging. And so what's happening is the top is we're saying everybody's casting our vote, but then we have to divide. In other words, we have to average out. So we have the center, x bar. So whenever you see a bar, that you should think of as like our average. So our average x, the center of our mass, is m0 over m. Well, so that's 22 over 3 divided by 6. Okay, well, you can simplify that. That's 22 over 3 times 6. And notice that we can cancel, because 22 is 11 times 2. And we say, okay, 2 goes into 6, leaving us with 3. So we have 11 over 9. And there we go. Now we should always stop and ask the question, is this reasonable? Well, let's think about intuitively what should be true. If I'm going here from a very thin to very thick, so thin to thick, where should my center of mass be biased towards? If it was constant density, it'd be right in the middle. So between 0 and 2, 1. So I should be biasing towards the thicker end. Now, if we think about the value of 11/9, that does bias towards the thicker end. So that's good. It matches our intuition. We should be near to where there's more mass. So, all right, good. Well, not so bad. Now remember this answer, because the next problem is going to be a little different. So, here we go. For the rod with density 1 plus 2x for 0 less than or equal to x less than or equal to 2, determine where the rod would need to be cut so that each piece would contain 50% of the mass. All right, now, interesting. What do we know? So if you've done the previous problem, so I'm going to assume that you've done the previous problem, we've actually done some of the computation that we need. So in the previous problem, previously in doing calculus problems, we saw that the mass of this is equal to 6. And just for reference, the way we do it is it's the integral from 0 to 2 of our density times our dx. And you work it out, you get 6. Okay. So, now what are we trying to do? Well, the picture should be, we have our situation where we have our rod. It gets thicker as we go closer to 2. And what we're looking for is we're looking for that special spot where somewhere around here, well, let's say, I don't know exactly where, but I'm looking for here where, lo and behold, 50% of mass is on one side and 50% is on the other side. So the question is, where do we cut it? So that's what we're looking for, is where to cut to get that nice effect. So let's suppose we don't know, because we don't know. So it's not too hard to imagine that we don't know what the answer is. But we'll call it something. We'll call it B. So B is something that we're going to try to find. And what do we want? Well, we want that the integral from 0 up to B of 1 plus 2x dx, and this is the mass from 0 less than or equal to x less than or equal to b, we want that to be 50%. Well, we know the total mass is 6. So if we want 50% of that, we should set this equal to 3. All right, so, well, we proceed. Here we integrate. We'll get x plus x squared and evaluate 0 up to b, which is b plus b squared. So we're looking for some number b where when you add the number and the square of the number, you get 3. Another way to say it is we want b squared plus b minus 3 equals 0. Well, does it factor? No, not nicely. See, if it were going to factor, it would have to be a 3 times a 1. but there's no way to add or subtract 3 and 1 and end up with 1 in the middle. Does that mean we give up? No, not yet. We think, okay, is there another way to solve quadratics if we can't factor? Some sort of a formula for quadratics. A quadratic formula, if you will. Yeah, of course, there is a quadratic formula. So, how does it go? Well, it says, if you want the solution, what you do is you take minus the coefficient of that term, so negative 1 plus or minus the square root, and you square that, 1 minus 4 times 1 times negative 3. Well, that'll be plus 12, right? 4 times 3, and the minus makes it, well, normally it would be a minus, becomes a plus. All over 2 times what's in front of there. Of course, that leads us to two possibilities. Minus 1 plus square root of 13 over 2, or minus 1 minus square root of 13 over 2. But we know in our picture we need to be between 0 and 2, so it's not going to be that one. So we end up with the square root of 13 minus 1 over 2. Now, at this point, you might be a little bit, is it? That's kind of a weird number. Yes, it is a weird number. And that's one of the things we want to emphasize. If you go back to the previous problem, and you said, where's the center of mass? We'll just pull it up really quickly. We said, look, 11/9. What a nice number. And it was very pleasant. And here, when we said, where's that 50% cutoff mark? Well, it's negative 1 plus the square root of 13 over 2. What? So, you might ask, is it reasonable? Now, I don't know the exact value of square root of 13, but it's going to be somewhere between 3 and 4. So let's say it's 3.5. We'll split the difference. So 3.5 minus 1, around 2.5, divide by 2, about 1 1/4. So it meshes with the picture, because we should be somewhere between 1 and 2 if we're looking for that cutoff spot. But it does go to show you that center of mass is not the same as saying, where's the 50% cutoff mark? It's a very different concept. So you have to make sure you sort of separate the two ideas. And between the two of them, I recommend center of mass is easier to figure out. All right, good. Woo. Nice. Nice way to start. Okay, on to our next problem. Find the center of mass of the region where y goes from 0 to 1 minus x squared, given the density of the region is 1 plus x. Okay, well, let's think about the picture here. So, we have our shape. Well, we have 0 less than or equal to y. So this is y equals 0. It's the x-axis. 1 minus x squared is an upside down parabola. So, our region is the space in between. All right, well, that's not so bad. So here we go. Here's our region. All right. Now, what are we after? Well, we're after our center of mass. Now, one of the things we might say is, okay, is there any symmetry? You see, center of mass, you need to find an x-coordinate and a y-coordinate. We're looking for both x and y. And you say, aha, look, there's symmetry right there, right? Because you just pick it up, turn it over, put it down. Is there? Is there symmetry? The answer, let's be careful. The shape is definitely symmetric. No doubt about that. The shape is symmetric. But look closely. Look at the density. It's 1 plus x. So what does that tell us? Well, it tells us that over here near negative 1, it's very thin. But as we move to the right, you'll see near x equals 1, our density is near 2. So as we go from left to right, we sort of get thicker and thicker and thicker. So what's happening is, well, if we could somehow shade, not very dense here, but then as we start moving along, all of a sudden, very dense. So it's denser towards one side. So that means when we pick it up and turn it over, put it back down, the densities don't line up. So there is no symmetry to save us on this problem. Okay, that means we really got to put in all the work. But that's all right. We don't mind a little bit of work, right? It helps us. It helps us make sure we understand the material. So, what are we going to find? Well, we're after our center of mass, so that's our x bar, y bar. And we know, for instance, that x bar, it's the moment with respect to the y-axis over m, and y bar, that's the moment with respect to the x-axis over m. So again, x bar, y bar, think of these as like the average x, average y. And of course, there's always that strange notation. You know, you're like, this is an x, but that's a y. What? Why do they switch? Well, you have to just think about the roles that are being played. So when we talk about moment with respect to y, we're saying, how far are you from y? And the answer is x. So that's why you have that situation going on. Now, what to do? Well, let's start with the mass. That's probably a good place to start. Now for mass, what do you have? You integrate, start to finish. So just integration is a way to say add up. And then we have our density. And we have our, okay, before we get too far, I want to be careful here. This is a little bit different than the rod because this is two-dimensional. So when I multiply density, I have to multiply by something two-dimensional, which is an area. And the area we should think of as happening here is what we get when we do a slice. So here's a slice, and we're going to cue off of that slice. So there's two parts to it. There's a height, and there's a width. Okay, so that's what we get. So height times width is area, area times density is mass. So that's the mass of that little piece. There is, on a side note, I am slicing vertically, and the reason I'm choosing to slice vertically is you'll notice that the density is a function of x. So we need to slice so that when we have our slices, we have to do it where we're integrating with respect to x so that our slices have essentially a constant density. That's why we choose to do things the way we do. I mean, at the end of the day, why do we choose to do anything? Well, it's so we can answer the question. That's why. Of course, sometimes that's very unsatisfactory, but it's also true. So density is 1 plus x. The height from bottom to top, well, that's up to the curve. 1 minus x squared, and the width is dx. So this becomes integral -1 to 1. Multiply it out, we're going to get the following. Well, 1 minus x squared plus x minus x cubed. Now, I want to do something to save work, but I don't want you to think I'm cheating here. So I'm going to explain two things really quickly so that what is about to happen, you're going to be like, okay, I believe it. I believe you're not cheating me. So here are the two things. It's actually not so hard to remember, but if you're integrating from negative a to positive a, any function which is an odd function, do you remember what happens? If it's an odd function, well, odd functions are functions like sine x or x. What happens is it all cancels out. So whenever I'm doing an integral of an odd function, and I'm going from negative a to positive a, that cancels out. If I'm doing the integral of an even function, negative a to positive a of an even function, I really just have to go from 0 to a and double. Now an even function is something like cosine or x squared, things of that nature. And it all comes down to symmetries. And so a quick reminder, so an odd function has something like this. So you say, hey, the part over here from 0 to a, part from negative a to 0, exactly cancel. An even function, we'll do something like this. You say, hey, look, the part from 0 to negative a exactly matches the part from 0 to positive a. So you just have to do one of them. How do we use this? Well, notice our bounds, negative a to a, negative 1 to 1. The x and the x cubed are both odd, so when we actually carry out the integral all the way, they're going to go to 0. So I'm just going to ignore them. And then the other parts are even, so I can say, well, look, I just need to go from 0 to 1 and double them. So 1 minus x squared dx. So this is using symmetry to collapse the integral down, just to help save ourselves a little bit of space. If you didn't do this, by the way, you still get the same thing. So I'm not saying that this is something you have to do. This is just sort of one of those, hey, why don't we save ourselves some work? Because after all, at the end of the day, we care about ourselves, and we want to make sure that we're taking care of ourselves. So this will be 2x minus 1/3 x cubed from 0 to 1. Well, it's easy to plug in 0. You get 0. When you plug in 1, 1 minus 1/3, that's 2/3. 2 times 2/3 is 4/3. Good. 4/3. That's our mass. So that's what goes underneath. So we have a 4/3 underneath there, and here we have a 4/3 underneath there. All right, well, now we've made some progress. Of course, now we have to do more, right? So, well, let's go to our m sub y. What happens there? Well, when we're looking for m sub y, it's a moment, and there, it's very similar. We just have an extra piece, it's location. But everything else stays the same. And for m sub y, how do we think of that? Well, if I want, here's my center for my little strip. The distance to the y-axis is x. So the only thing that happens here is that you have an extra x. X is for the location. And 1 plus x, 1 minus x squared dx. So I'm going to multiply it out. Integral negative 1 to 1. Every term gets an extra x. So it's x minus x cubed plus x squared minus x to the 4th dx. And now do the same thing we did just before. That is, anything that's odd gets knocked out. Pew, pew. Anything that's even, double up and go from 0 to 1. Now, you might say, well, why bother doubling up and going from 0 to 1? It's because I like plugging in 0. It's so easy to plug in 0. That's why I do it. That's why I do it. So we'll have integral x squared minus x to the 4th. So that's 2. 1/3 x cubed minus 1/5 x to the 5th from 0 to 1. Well, okay, now we'll have to do a little bit of math in our head. If you plug in 0, you get 0. When you plug in 1, you get 1/3 minus 1/5. Okay, so here's the math in the head, okay? So we said 1/3 subtract 1/5. So that would be 5/15. That's 1/3. Subtract 3/15. 5 subtract 3 makes 2. 2/15. But there's another 2 right there. So put it together, and we're going to end up with 4/15. All right. So that tells us that this part right here is a 4/15 m sub y. All right. Good. Well, one more integral to find, a little bit of cleaning up, and we'll be done. All right, well, let's tackle the next one. Here we go. So the next one is very similar. It's the moment with respect to x. So it's the same generic formula. I won't write it down again. The only thing that changes is how far are we from the x-axis? Well, it's going down to the x-axis. So our distance to the x-axis is going to be sort of at the halfway up mark. And in general, it's the average between the top curve and the bottom curve. So I need to go halfway up to the curve 1 minus x squared. So it's 1/2 1 minus x squared times 1 plus x times 1 minus x squared dx. So our location, our density, our height, our width. Okay. This is we're going to need to be patient here. So we have a 1/2 integral -1 to 1. If we multiply this out, well, it's actually not so bad. See, what we do, we know what 1 plus x times 1 minus x squared is, because we did that. So we'll multiply that by 1, which would give us 1 minus x squared plus x minus x cubed. And then we'll multiply it by negative x squared. So minus x squared minus makes plus x to the 4th minus x cubed plus x to the 5th. Okay, so this is, if you multiply it all out and you didn't bother to group terms, that's what you'd end up with. Okay, equals. So now we're going to use symmetry. We go through, anything with an odd power gets knocked out. So x minus x cubed, and then our x cubed and x to the 5th. So those terms get knocked out. Okay, good, good. Now, double. Well, since we have a half and we double, that just gets us to 1 times, go from 0 to 1. And then you have 1 minus 2x squared plus x to the 4th. All right, we did it. We made it. Well, almost. A little bit more work to do. So now, integrate, and then we're home free. So here we go. This will be x minus 2/3 x cubed plus 1/5 x to the 5th from 0 to 1. Well, plug in 0, you get 0. Plug in 1. That's what we might want to do. Not in our heads. We're going to get 1, and I see 3 and 5 shown up, so I'm going to write that as 15 over 15 minus 2/3, so that'll be 10 over 15 plus 1/5, well, that'll be 3 over 15. So it'll be 18 minus 10, which should be 8/15. So that's our y bar, 8/15. Okay, well, now we need to clean things up. So let's, we'll start with y bar since it's just right here. 8/15 over 4/3, that's really the same as 8 over 15 times 3 over 4. Well, 4 goes into 8, and 3 goes into 15, leaving us with 2/5. The other term, for x bar, well, we have 4 over 15 times 3 over 4. Again, that 4/3, it came 3 over 4 because it moved up, we flipped it over. The 4's cancel, 3 goes into 15, leaving us with 1/5. So our answer is 1/5, 2/5. And there we go. There's our center of mass. And we're done. Wow. Great. Wonderful. Now, is it reasonable? Well, we can kind of eyeball where 1/5 and 2/5 would be. 1/5, 2/5. Well, 2/5 is not quite halfway, so it's something like there. And we ask ourselves, okay, we check, is it roughly within where we expect the center to be? Well, we should definitely have it biased towards the right. That's a good sign. It needs to be within the shape. Okay, that's another good sign. And I say it has to be inside the shape because of the nature of the shape. This is a shape without holes. But, on the other hand, there's also things such as, if we look, well, it should be roughly halfway up and down. And yeah, this looks pretty good. If anything, it'd be a little bit below halfway down. Well, that's exactly what's happening here. So, good. Everything looks good. Reasonable answer. So, on to our next problem now. Wow. By the way, using symmetry, good thing to do. Symmetry is a wonderful tool in mathematics. Not just for integration, but one way to think of symmetry is saying, hey, let's reduce the problem down. And so symmetry is an important tool. Look for symmetry wherever you can. All right. Well, find the center of mass of the region, 0 less than or equal to y, less than or equal to 1 minus x squared, given the density of the region is constant. Okay. Well, this sounds familiar. We probably should have started with this one. It's the same region, but what do we see? Well, what we see is that our region might be the same, but our density is constant, which means it's a uniform constant value. So, what does that give us? Well, look at the shape and ask, do we have symmetry here? Well, we had symmetry before in the shape, but now, if we pick it up, turn it over, put it back down, it's also symmetric with respect to density. And by that, one way to talk about it is we say, this line right here, we call this a line of symmetry. And what we mean when we say something is symmetric with density, we say, if you have a little piece here, when you flip it over, and you say, where does it go to? These densities are going to match. So that's what we mean when it's symmetrical. That when you cross through that line of symmetry, the density remains the same. Well, our center of mass will always be on any line of symmetry. And therefore, we can conclude the following. By symmetry, we know our center of mass, I'll just abbreviate center of mass, that's COM, lies on the line x equals 0. So we lie on that line. Therefore, that tells us automatically that our x-coordinate is 0. So we're halfway done. We've already found one coordinate for our center of mass. Woohoo! Nice! Well, now we have to find our second coordinate for our center of mass, which is our y-bar. And for that, well, we don't have any more symmetries. We've taken that as far as we can go. So for y-bar, well, it's our moment with respect to x divided by our mass. So let's begin. So what do we get? Well, what's our mass? Our mass will be, we'll mark some things here just for reference. We're going to add up, start to finish. It's going to be our density, it's going to be our height, it's going to be our width. Really, it's density times area because it's a two-dimensional region, so you take density times a two-dimensional measurement. So integral at -1 to 1, and the density is always 1, so we get 1 minus x squared and dx. Well, we can just integrate that. Let's just use the fact that this is symmetric. So we can say, well, look, this is really 2, integral 0 to 1, of 1 minus x squared. And that's because our function 1 minus x squared is even. It doesn't feel like it saves a lot of work, but I really like plugging in 0. That's why when I can, I like to get 0 involved in the problem. So that's 2, and then we get x minus 1/3 x cubed. Evaluate that from 0 to 1. So that's really 2 times 1 minus 1/3. 2 times 2/3 is 4/3. And good, we've got our mass. So there's our mass, 4/3. Okay. What about our moment? Well, let's think about that. By the way, if you're thinking about, hey, isn't the previous problem, didn't we get the same exact amount of mass? Should we be suspicious? It turns out if you could think of the plate, this is just a side note, but if you think of this, it's a two-dimensional region, but think of it as sort of sometimes there's a very fancy word they use, laminar plate. So think of it as like a thin plate. And so currently it's just height 1 constantly. Well, what you can do is you can imagine that you take your thin plate and you slowly slice up. And so you start at height 0, and when you hit the halfway point, you're up to the height of the plate. If you take that piece and turn it over on top of the other one, then it turns out that what you'll get is that if you slowly start at the bottom at 0 and then work your way up to double the thickness of what you started. And that's exactly what we had before. So essentially what's happened is that somehow we've transferred mass from sort of one side to the other side, but the total mass is the same when we compare the two different shapes from this problem versus the current problem. Okay, that was an aside note, and if that sounded like rambling, that's okay. You just say, okay, that was Steve rambling, all right. Now we go back and do the real part. Okay, so now we do the moment. So we're slicing, and we can slice either way here, but because we have a function of x and it says our density is a function of x, it makes sense to do our vertical slicing. So our moment with respect to x, well, adding up, you add a location, a density, a height, and a width. So it goes -1 to 1. What's our location? Well, we think of the center for that one little piece and say, how far is that from the x-axis? Well, it's halfway up. So 1/2, 1 minus x squared. Our density is 1 and 1 minus x squared. And lo and behold, this is all even. Everything is even powers. So we can again double. And so we get that this is integral 0 to 1, expand out 1 minus 2x squared plus x to the fourth dx. And that becomes x minus 2/3 x cubed plus 1/5 x to the fifth, and evaluate from 0 to 1. Well, okay, so that's 1, 15/15 minus 2/3, 10/15 plus 1/5, which is 3/15. Put it all together, you get 8/15. And you might be having some, whoa, this is feeling really familiar. Really familiar. Well, it probably should. And it goes back to that picture, which I have a hard time trying to explain. You see how we took that mass from one side and we flipped it over and turned it to the other side? Well, what's happening is in terms of the total mass at any portion for y, we have neither added or subtracted mass. We've just sort of moved it around at that level. And therefore, from the perspective of the y moving back and forth, it says, hey, there's still the mass at every height y that there was before, so the center of mass with respect to y will still be the same. And so that's why we'll see, for example, 4 goes into 8 and leaves us with 2, 3 goes into 15, leaving us with 5. We get the same y coordinate for the center of mass. But the important thing is the x coordinate is different. And the moral, if you compare this problem and the problem we did just before this one, you can see that we really love when there's symmetry, because it really saved us a lot of work. And symmetry includes both symmetry includes both with respect to shape and with respect to density. So if you don't have that symmetry with respect to density, you got to do the work. You just can't say, aha, it's going to be 0, because we saw, no, it doesn't mean that it will necessarily be 0. You don't know until you do the work. Okay. Well, let's try another problem. So, a thin, flat plate is bounded below and above by the lines y equals 1 and y equals 3. Okay, so there's y equals 1 and y equals 3. And bounded to the left and right by the curves, y equals 1 over x squared. Okay, there we go. And the plate's density at any point x, y is given by our density is y. Now, find the coordinates of the center of mass of the plate. Now, what does this mean? Well, what it means is that if we're down here, lower value, we're less dense. While we're up here, higher y value, we're more dense. So if we were almost thinking of it as a plane with a little bit of thickness, as we go from the bottom to the top, it's sort of getting thicker as we move up. So it's getting from thin to thick as we move up. Now, the question, of course, where is our center of mass? Well, when we're thinking about center of mass, we look at it. First thing we always ask is there any symmetry? And here, I think we can spot a nice symmetry, namely this line. So x equals 0, this is a line of symmetry. And remember, you always have to check two things. Is it symmetric with respect to the shape, and is it symmetric with respect to density? In other words, if you picked it up, turn it over, put it back down, would you not be able to tell that you picked it up? That's symmetry. You can't tell if you pick it up, turn it over, put it back down. And in this case, we wouldn't be able to tell. So it's like perfect. This part here tells us automatically, with no work, that our x coordinate has to be 0. So it saves us a step. It doesn't mean we're done, because we still have another coordinate we have to find, which is the y coordinate. Well, let's think about that. So what do? For the y coordinate, we do the following. We say y bar is our moment with respect to x divided by our mass. So we're going to have to figure these pieces out. Let's start with the mass. So mass, we're adding up A to B. We take our density times our width times our height. Now, you might notice, wait a second, why did you transpose height and width? Well, it doesn't really matter. We just need to have them both in here. But what's going on with this? Well, we need to slice in a different direction. We have to slice horizontal. We have to. We don't have a choice. And so we're going to be integrating in such a way that the little change here, the little thickness, is going to be a height. Now, you might be saying, Steve, I object. Why do we have to? Why are you so adamant that it must be a horizontal? Why couldn't it be a vertical? Okay, good question. So I think that this is a good place to point out why it couldn't be a vertical slicing. So let's, for a second, look at this picture. And suppose we were to do a vertical slice. I'm just going to do a little dot here. Just to emphasize, this is not what we're doing. This is just for our conversation here. If you look at the picture, what do you notice about the density over the range of the slice? Well, the density at the bottom, and recall this is y equals 1, would be 1. Density at the top would be 3. In other words, the density varies a lot. When you have something varying a lot, it can't be a part of the small piece, because the idea of integration is that the small pieces, nothing changes very much in the small piece. So that throws out our whole approach, because the density varies too much. On the other hand, when we slice horizontal, as we do here, notice that our difference in density, well, whatever this is, for bottom value for y, this next height for y is super, super close. So if we look at y and y plus a little tiny bit, the density hasn't changed hardly at all. And that's why you're like, oh yeah, the density is essentially just what it is. It's y. So this is why we have to do horizontal slicing. Okay, so now back to our regularly scheduled problem. So where do we go? Well, we think about our pieces. We have our density. All right, that's not so bad. That's y. We know where we start and stop, by the way, 1 and 3. We know our width. Well, do we? We'll come back to that in a second. We know our little height. Our height is just this little piece right here. How much our little height is of a slice. That's our dy. Now, what about our width? Well, we say, hey, it's 1 over x squared. Wrong. Why? Well, because we have to have everything in terms of y. It's an integral with respect to y. That's the dy part. So if you're integrating with respect to y, everything has to be in terms of y. So when we come here, we say y equals 1 over x squared. Well, that's y as a function of x. So you can say x squared is 1 over y, or x is 1 over root y. Now that's if I'm on the positive side. On the negative side, x would be minus 1 over root y. So the width is going to be the length between these two sides. So you take the larger value for x, subtract the smaller value for x. Right minus left. 1 over root y, subtract minus 1 over root y, leaves us with 2 over square root of y. So we now have the following. This will be integral 1 to 3. We have a factor of 2. Then you have a y over square root of y. Well, that's also known as square root of y, or y to the 1/2. All right. Well, we can integrate that. That's a 2. We'll have y to the 3/2 multiplied by a 2/3 and evaluate from 1 to 3. So what does that turn out to be? Well, 2 times 2/3 is 4/3. When you plug in 3 to the 3/2, well, it's 3 to the 3/2. There's not really much you can do. You can do a little bit. Notice this is like a square root of 3 times a square root of 3 times a square root of 3. If you combine two square roots of 3 together, it leaves you with 3. So you could write it as 3 square root of 3 minus 1. Okay, well, I think it's about as close as we can get. Now, we're not done because that's just the mass. That's what goes in our denominator. So 4/3 times 3 square root of 3 minus 1. Now we have to do our moment. So how do we do that? Well, our moment is going to be very similar computation, except we're going to add one more piece. When we have the moment, there's a distance part or a location part. So we have an extra term. Now hopefully the extra term won't be so bad. What is it? Well, what we do is we say, okay, imagine that you have the middle of that strip. That center of that strip is the center of mass for that strip. And that's why we want our strip to have constant density. So we can just say, oh yeah, once it's constant density, I know where the center is. So when I'm talking about the moment, and I forgot to put my subscript here, subscript tell me where I'm doing it with respect to. So moment with respect to x would be how far I have to go down to get to the x-axis, which is y. So our location is y. Everything else stays the same. So, in other words, we still have our density as y, we still have our width is 2 over root y, we still have our height is dy. So what this becomes is integral 1 to 3 of 2y to the 3/2. Okay, so that's 2 times 2/5 y to the 5/2. Evaluate from 1 to 3. Well, okay, that's 4/5. And then 3 to the 5/2. Well, you can do the same thing, right? Because there's like, we have 3, square root of 3 5 times. 2 of them together make a 3. 2 more to make another 3. So there's a 3, another 3, and a root 3. So I can write that as 9 square root of 3, subtract 1. So there we go. 4/5 9 root 3 minus 1. Well, can we do anything? Not really. It is what it is. And maybe it's not the prettiest looking thing. There is a small thing we can do. You'll notice that the 4's, they're in good shape. We can actually cancel the 4's. And this 5 you can move downstairs. And this 3 you can move upstairs. So, at the end, our answer, because we have to find a center of mass, so our x-coordinate is 0. Notice how quick we got that compared to the y-coordinate. And our y-coordinate would be 3 times 9 root 3 minus 1 divided by 5 times 3 root 3 minus 1. And, well, it's a little bit hard to get a reading on what is that value. But, well, sometimes they come out this way, right? A little bit hard to control. This is an interesting problem just because it says, hey, we might need to turn sideways, not do vertical slicing, but do horizontal. And do we have to put a lot of thought into it? And the correct answer should hopefully be no. See, it's the same principles in play. So as long as we understand the aspects, the density, the width, the height, or location, density, width, height, and say, okay, look, just transform it to the new setting. Life is good. Life is wonderful. All right, well, Okay, and that brings us to our last problem. Woohoo! We shouldn't be happy it's the end. Well, but we should be happy that we got to do fun problems. So, what's our last one? Find the mass of the wire with the shape y equals a half x squared, where x goes from 0 to square root of 3, given that our density is 2x cubed. Now, a couple of things to note. We see a couple of key words, at least one word jumps out. Wire. Well, what is that telling us? It tells us that it's a one-dimensional type problem. And so we've done one-dimensional type problems, which are rods. So a wire is where we take a rod, but then we just sort of bend it. So that instead of being a straight thing, it's a slightly bent thing. But the principles are still the same. That's an important thing. Another nice thing that we see is this is not a center of mass problem. So no moments, so woohoo! Good to avoid the moments for the time being. Not that those are bad, just a little bit of extra work, right? So let's draw our wire. So our wire says we have our curve, the wire that it's bent, is a half x squared. So it would look something along the lines of the following. A half x squared. All right. And we go from 0 to root 3. Now, we also see that there's a density involved. And we see, for instance, at 0, there's density 0. By the time we hit to root 3, well, it's some bigger number. So pictorially, we can think of it as this is a wire that gets a little bit thicker the further over we go. So that's sort of the idea, is it's very thin and it gets thick as we move it on up. And we're after the mass. So, all right, so how do we approach this problem? Well, if it were just the rod, what we would do is we would find the mass by doing the following. Add up, start to finish, a little bit of density times length. That's how we would do it if we were doing a problem with the rod. But when we're doing a problem with the wire, what we do is we add up from start to finish the little bits of density times length. In other words, it's the same setup. You see, once you have this, it's saying this is the underlying principle, then we don't have to memorize like 100 formulas. We just say memorize the principles. And that makes it so much easier. It saves a lot of space. And then you can memorize all the useful things. I don't know what an example of a useful thing is, but there's more space for it now. So whatever it might be, it depends on the person. All right, so let's think about what's happening here. For us, well, the start and the finish, easy. 0, root 3. No problem. The density, given. 2x cubed. Easy, no problem. Now the length. Here's where we differ from the rod. See, the rod goes in this straight line, so when we chop into little pieces, the length is just a little bit of change in x. But when we're curving up, well, the length is a little different. So what we have to think about is we have to think about, okay, if we're doing our little chopping, what's the length of a little piece? And for that, we say, we've done this before. We actually figured out arc length. And if you go back to arc length, it's the square root of 1 plus the f prime of x squared times dx. If you think about what's happening with the rod, where f of x is 0, it just simply says, oh, it's dx. So this is the more general formula. So for us, we say, all right, what's our derivative? Well, the derivative of a half x squared, that's our f of x, is x. So this would become square root 1 plus x squared dx. And now we have all our pieces. We get 0 to square root of 3, 2x cubed, square root 1 plus x squared dx. All right, we can begin the fun. And it will be some fun. How do we integrate this? Well, let's be optimists. We think we can integrate it, so let's proceed as though we can. We know some things we can. There's no trig right now, and algebra, about the only thing is like, well, maybe we can do something with the square root and the plus. And the answer is no. We're not even going to yield to that temptation. We want to learn to respect the square root. By the time we're done with calculus, us and the square root are going to have a good mutual respect for each other. We respect that square roots are difficult, but square roots respect that we will treat them gently, lovingly, and with proper algebra, so that we'll get along. All right. So there's not many things left, but there is one important tool left, and that is substitution. Substitution is our go-to tool to make things simpler. And when we're thinking about substitution, well, substitution is an inside job. So one thing to look for is a function on the inside. There's a good candidate here. 1 plus x squared is a great candidate for being the inside function. So for now, let's try it. U equals 1 plus x squared. Well, if we did that, du would be 2x dx. We say, well, we've got the dx. We even have the 2. Wow, almost as if they anticipated our needs. But we have x cubed, not x. Well, the good news is if we have x cubed, we already have x. So I'm going to think of this x cubed as x times x squared. And say, well, look, I'll take one of the x's, and that'll be good. That leaves me with an x squared left over. What can we do with that? Because remember, whenever we do substitution, if I start with x, everything has to change to u. There's no mingling afterwards. Everything changes. So, can we replace the x squared, this new piece here, in terms of u? Well, yeah, it's not so bad. We know u is 1 plus x squared, which tells us that x squared is u minus 1. So what do we get? Well, we get, this is the integral. The 2x dx becomes du. The other x squared, to make up that x cubed in front, becomes u minus 1. The square root of 1 plus x squared comes square root of u. And the bounds. Don't forget the bounds. When you're doing a different integral, always update the bounds as you go forward. And then you'll never have to go back. It's just a good habit to get into. Update the bounds. Plug in 0. 1 plus 0 squared. 1. Plug in root 3. 1 plus root 3 squared. Well, that's 1 plus 3. 4. Oh, those are nice numbers, especially since there's a square root involved. Okay. So 1 to 4. We can now, it's not so bad, we can distribute through. So this would become u to the 3/2 minus u to the 1/2 du. So that's, we can integrate u to the 3/2. Well, that's u to the 5/2, multiplying front by 2/5. And now subtract u to the 1/2, that's u to the 3/2, multiplying front by 2/3. And we can evaluate from 1 to 4. Well, this is going to be some interesting numbers, but at least we're getting there. All that's left, there's some algebra here, some arithmetic. Okay, 4 to the 5/2. Now, of course, if you know 4 to the 5th is 1024, and the square root of 1024 is 32, that's great. But probably it's easier for you to say, hey, the square root of 4 is 2, and then take that to the 5th power, 2, 4, 8, 16, 32. So you have 32 times 2 makes 64 fifths. Subtract 4 to the 3/2, square root of 4 is 2, 2 cubed is 8, times 2, 16 thirds. Now when you plug in 1, super easy. It's just the coefficients, 2/5 and 2/3. All right, so that's going to be what we get when we evaluate. Well, let's common denominator is 15. 64 over 5, well, I need to multiply by 3 over 3. 64 times 3 is, of course, 192. All right, over 15. To get 16 over 3, well, I need to multiply by 5. 16 times 5 would be 80. Don't forget the minus. Minus 80. Then minus 2 over 15, we'll multiply by 3. That'd be 6 over 15. Don't forget the minus, so minus 6. And then here, 2 over 3, I've put it into over 15. I have to multiply by 5. 10 over 15, minus minus, it's a plus. Be careful here. This is a case where a lot of people forget that minuses distribute. We're going to be careful because we want to make sure we don't lose anything. After we've come this way, we definitely don't want to lose anything. Well, let's see, what do we have? 192 subtract 80 would be 112. Subtract 6 more would be 106. And add 10 more would be 116. And then downstairs, 15. Can we simplify? Well, it's not divisible by 5, we can tell, because of the last digit. And it's also not divisible by 3, because if you add up the digits, you get 8. In other words, the 1 plus 1 plus 6. That's not divisible by 3, so that means the original is also not divisible by 3, which means that's as simple as it gets. Now, you might say, is that really simple? Well, that we found an answer, that's a good sign. It's not too hard to come up with a problem where we can't find answers because, well, integrals are challenging. But the ideas behind them are wonderful. And it's so fun that we can do problems like this. Well, all right, it's been a lot of fun. Keep up the practice. You're doing great. And we'll keep doing some more problems and do different applications, different things, learn a little bit more about integration. There's a lot of good stuff ahead. So I hope you come back and I'll see you again.